Well, good afternoon, everybody. It's my honor to welcome you all to today's seminar in the context of the C3.ai Digital Transformation Institute. My name is Kostas Panos. I'm a professor of electrical engineering and computer sciences at UC Berkeley, and I'm also the co-chief scientist of the institute. So our institute is relatively new. Many of you know about it. We started a few months ago. But our mission is to attract the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. The Institute is actually a collaboration by several universities and other entities. It is funded by C3.ai, which is a major participant, and Microsoft. But we also have colleagues from University of Illinois at Urbana-Champaign, UC Berkeley, the two universities that are leading the effort, with a very strong participation by Carnegie Mellon University, MIT, Princeton University, the University of Chicago, Stanford University, NCSA, and the Berkeley Lab. As I mentioned, this is a seminar series, and you can see here the upcoming events. We meet weekly at 1 p.m. Every Thursday, Pacific time. And you can see the very exciting sequence of presentations that we have lined up for the several weeks to go. The emphasis, as you will notice, is of course machine learning and digital transformation in general, but you will see many presentations surrounding COVID-19. This is not an accident because as we started the Institute, we funded many proposals on that theme a few months ago, and many of the presenters are from that group. But of course, we're not limited to that. So you can see here the presentations going to the end of the calendar year, but we have presentations now lining up for the spring semester as well. In addition to the weekly presentations, we hold periodic workshops about once a month. This is the second workshop that we'll be holding that is actually happening next week, October 19th to the 21st and the 23rd. And it's going to be going from 9 a.m. to 2 p.m. Pacific time, noon to 5 p.m. Eastern time. And it is a very exciting subject. It's talking about the analytical foundations of deep learning. And of course, the issues of interpretability and performance guarantees are very important. So this workshop has been organized by Ma from UC Berkeley and René Vidal from Johns Hopkins. And it has a great collection of speakers, as you can see here, from many universities beyond our immediate network, as you can see. And so I hope that you will be able to attend. The first workshop that we had a few weeks ago was also a very, very successful event. So I think you'll enjoy attending this one as well. So getting closer to today's event, the format is pretty straightforward. We have a 40-minute presentation by our speakers. Try to reserve about 15 minutes Q&A. And in the Q&A, you can use the Q&A feature of Zoom to ask questions in writing. If you have seen the question that you would like to ask already being asked, you can upvote it so that it gets priority. And we will try to answer as many questions as the time will allow. So today, the presentation, the title is COVIDScholar. It is an NLP hub for COVID-19 research literature. And we have two presenters that will be contributing. One is Professor Gerbrand Ceder. He's a Chancellor's Professor of Material Science and Engineering at UC Berkeley. His research is in computational and experimental materials for clean energy technology and materials genome approaches to materials design and synthesis. He has published a large number of scientific papers, holds more than 20 US and foreign patents. He's a member of the US National Academy of Engineering and the Royal Flemish Academy of Belgium for Science and the Art, a fellow of Material Science Research Society and the Minerals, Metals and Materials Society, and has received awards from the Electrochemical Society, the Materials Research Society, the Minerals, Metals and Materials Society, and the International Battery Association. He's a college scientist for new battery technologies at the US Department of Energy's Joint Center for Energy Storage and chief scientist of the Energy Frontier Research Center at the National Renewable Energy Laboratory, or NRL. So Professor Ceder will be giving the presentation with Amalie Trewartha, who is a postdoctoral scholar in his group at Lawrence Berkeley National Laboratory. She started as a nuclear physicist before moving into materials in 2019 with a focus on machine learning. Her interests include the application of NLP, natural language processing, to scientific literature, and building thermodynamically motivated machine learning models for materials property prediction. So with that, I'm honored to turn it over to our presenters for the presentation today. So we'll stop sharing so you can take over.
Great, thank you, Kostas. Let's see, Amalie, can you bring up the slides? There we go. Great, thank you. So as was already mentioned by Kostas, we'll be tag teaming this presentation, but really most of it will be given by Amalie, who's really the leading effort on COVIDScholar. I'm a total pretender when it comes to COVID, and what I was going to do is just give you a few introduction how a materials group gets into COVID and how that led to COVIDScholar, and then you'll get the real story from Amalie. Can you go to the next slide, Amalie? Yeah. So a bit of background. What we really are as a group is a materials design group. We design new materials mainly in the clean energy space, and have done that for over 25 years, I would say, until a few years ago, in a very classical approach, sort of the classic deductive logic physics approach. So we solve big equations, in our case, the Schrödinger equation of physics, and use that to predict materials. What we have found, can you click next, Amalie? I think what we have found a few years ago is that this works really well for problems where you understand the physics and have equations to solve it, but that we were more and more running into problems where we did not understand the underlying physics or chemistry. So that's how we got into data-driven approaches, right? And this is really what data-driven approaches are so good for, right? If you know the equations that solve input to output, then there's maybe not a whole lot of points for a data-driven approaches. So I'll show you sort of one example that we were working on that then led to COVIDScholar. If you do next slide, Amalie. So a typical example for us, we have become extremely good at designing novel materials. And again, that's done by solving the equations of quantum mechanics. We can predict many properties of materials now before they are actually made. So creating essentially a virtual testing lab of materials. But what we more and more are stuck with, what is sort of our gating problem now, is that when we try to come up with completely novel compounds, we have no idea how to make them. You know, there is no Schrödinger equation equivalent for synthesis routes. There is nothing that tells you solve this set of equations and you will know how to make something. And what's really fascinating and important to know is there is an enormous amount of what I would say truly groundbreaking new materials in the pipeline, in the design pipeline, that have not been made yet as of today. Things that would revolutionize, for example, the energy storage industry, which is one of my pet research topics. And the problem with synthesis of materials is that there is neither an existence proof nor a non-existence proof. So you can keep on trying as much as you want. So if you go to the next slide, Amalie. So that's what brought us into data. What we thought, how do people learn synthesis? If I ask a student or a postdoc to make a new material, they use a little bit of their basic chemistry knowledge, but what they really do is go and read papers on related materials. They look at compounds that may be similar, either chemically or structurally similar, and then they try to see, well, how should I modify that synthesis route to come up with something new? So we asked ourselves the question about 3-4 years ago, whether we can codify that and essentially build a machine learning tool or an AI-driven tool for synthesis. If we could learn the laws of inorganic material synthesis. Well, it turns out that turns into an NLP problem very quickly, a natural language problem, because there is no data on synthesis. There is no useful data sets, codified, standardized data sets for how to make inorganic materials. So this is not like being Facebook or Google where you have tens of millions of data points. We had none. So that led us to develop all the NLP techniques to do scientific information extraction. So we got access to several millions of research papers in the material science world and build essentially a pipeline to extract synthesis recipes. This was actually inspired by an article I had read I think in the New York Times by somebody who had built an AI model for cooking, had actually made a machine read cooking books, which is a lot easier than chemistry, let me tell you. And then this thing would suggest new cooking recipes if you sort of specify the dish. It turns out in reality, it's a lot harder with chemistry. This took us over 3 years, a lot of AI and NLP work. And the reason is that extracting chemistry has to be very precise. You have to understand relations between aspects in text. For example, if you have operations, you have to see which attributes they have. If you grind, say, as here shown on the slide, for how long is it? Is it a grinding media? But we are now to the point where we can, we have tens of thousands of algorithmically formed synthesis recipes. So these are things that then you can operate on with computational technology to either data mine and machine learn from the rules of synthesis, or to actually have robots drive synthesis themselves. So that's how we got into NLP. That's how we sort of dealt with sort of large data sets. And then COVID happened. And if you go to the next slide, Amalie, I'll let you take over. There were a few adventures into other types of knowledge gathering techniques in material science. But then ultimately, COVID happened and Amalie got a team of people together. This is across 3 research groups, Christine Pearson's group, my own, and Anubhav Jain's group, and decided, hey, we should do this. We have all this technology already ready for materials. Why don't we do this for COVID? And so, Amalie, I'll let you take over from here, and I'll be around for questions and filling in once in a while.
Okay. Thanks, Gerd. Yeah, so maybe the more direct precedent for the work we're doing in COVID with COVIDScholar was this website we put up called MathScholar, which was a search engine we built for the material science literature using the NLP techniques that we had developed in the context of synthesis recipes. And so it would let you do things like search on materials and search on synthesis types and so on. It just had more power than existing search engines using NLP. And so on the basis of that, we got approached by our colleagues at the Innovative Genomics Institute here at UC Berkeley fairly early on in the pandemic, who were having a little bit of trouble staying on top of the enormous volume of COVID research that's coming out. And I have a plot here of the cumulative count of COVID publications over the course of 2020. And already by April, which is by the time we started this, there were literally tens of thousands of pieces of research emerging on COVID, which is well beyond the ability of sort of the traditional methods of literature engagement to keep up with. And not only is it the volume of research, something that really characterizes the COVID research is how diverse it's been. Practically every field has had some degree of COVID research. I mean, as you can see from the plot there, there's strong representation from physical sciences and humanities and social sciences, as well as what you might expect from biological and chemical sciences. And so just wanted to make a point about the volume of research emerging. These are the titles of the papers that came out yesterday. It's just an enormous amount of research. There's, at this point, over 300 articles every single day. And this is, for fields that are used to seeing maybe 20 or so papers a day, this is just impossible to stay on top of. This is also, it's not just about volume, it's also about the speed this is happening. Here's a little plot I made to sort of illustrate the extent to which the COVID community rapidly shifted their research efforts based on events. So this was based around the COVID-19 outbreak that happened in Italy earlier in the year. This was one of the first countries outside of China to have a large COVID outbreak. And I just made a plot here where, so in the orange, we have the number of cases in Italy. And this blue line here is the number of COVID publications referencing that outbreak. And so you can see here by like a month into the outbreak, there was already a few hundred publications that are emerging. This is an extremely short turnaround for scientific publishing, which normally is a paper might be a 6-month to a year effort. And so the focus of the research is shifting rapidly. New topics are emerging rapidly. And this is all happening on very, very short timescales. And the way that this has turned out to be possible is that COVID has seen a large shift away from traditional methods of scientific publishing around peer review. So in a traditional peer review approach, a manuscript will be sent off to a journal, which will then be distributed to peers for reviewing, edited appropriately, and then possibly published. And so the kind of the time scale on peer review is at least months, possibly up to a year, between a manuscript being submitted to a journal and its publication. And in the era of COVID, that's just not quick enough. If we had not had any publications on, say, the outbreak in Italy until June or July, the window of opportunity to have an impact on public policy would have been totally gone. And so the way the scientific community has shifted to deal with this is using preprint servers, which a preprint server will let a scientist like directly upload a manuscript to a server online and make it publicly available. And this will happen over the course of like 2 to 3 days rather than months. And so this has had the advantage that research is getting out there very, very quickly, but it has circumvented the normal role that journals play in terms of maintaining research quality and sort of highlighting relevant research. So this has kind of contributed to the problem scientists are having in picking out what is the important research, what are the important papers to be looking at. And this shift to preprint servers is very, very new in a lot of fields. So as late as March 2016, this New York Times headline about preprint servers says a handful of biologists went rogue and published directly to the internet in reference to them, which is a little bit dramatic. But the point is that like for most of these fields, they had never largely published through preprints before. The community was not used to dealing with preprints. They were not used to how to find them, how to take into account that they're not peer reviewed. So this is a very new experience for a lot of scientists who are working very quickly. And one of the sort of characteristic features about this is that there's a huge number of preprint servers. This is a list of 44 that I pulled up. The real number of preprint servers out there is much, much higher. And so this is research that's distributed over many, many sources, many of which scientists are not used to going to in the course of their normal reading of the literature. And so the COVID-19 literature is posing a lot of problems to the existing methods scientists had of engaging with the literature. It's very large, it's emerging very quickly. It's diversely distributed across practically every field. There's a large number of sources, and it's extremely time pressing, and research results are pertinent to public policy on the order of days or weeks rather than months. So as kind of a little case study of this, there was this article that emerged in April this year, COVID-19 antibody seroprevalence in Santa Clara County, California, which received a lot of buzz. This was like quite early in the pandemic, especially in the US. And this study was the first large-scale population testing in the US. And so obviously it had huge immediate public interest and received a lot of publicity. And the key finding of this paper was that for every detected reported case of COVID, there were between 50 and 85 mild undetected cases, which suggested that fatality rates were much lower than were being reported because of a large number of undetected cases, and that perhaps the effect of COVID would be much lower than had been previously thought. And this was seized on basically instantly by a variety of media outlets who used this to challenge the, at that point, controversial lockdown, and I guess still controversial lockdown, and using this to argue that lockdown was not a necessary strategy for dealing with COVID, and caused possibly a delay in the lockdown being instituted in various areas across the US. But then a couple of weeks later, it turned out that there were some fairly serious flaws in this study. Within a few weeks, they had adjusted the results of this study. There were issues with their sampling, there were issues with their testing. And the results were dramatically changed to massively reduce the number of unreported cases per reported case and to be more in line with what we now know about how serious COVID is. But this was kind of too late by the time this happened. And I remember when this study came out, there was a lot of buzz before it came out. And I was on a call with a group of COVID researchers, and they instantly knew that this study was hugely flawed. But that message didn't get out there until well after this study had had an effect. And so this is kind of all suggesting that we need to find new ways of engaging with the research literature in the age of COVID-19. And so kind of what we have done around this is this project COVIDScholar. So we have built this sort of single stop COVID-19 research search engine that has all COVID-19 relevant research across a variety of fields. We use NLP to help researchers locate exactly what they're looking for, to suggest research they might have overlooked. And we get all relevant papers up within a day of their appearance online. And so this is always a risk, but I was kind of hoping to do a live demo of the site quickly. Yeah, so here's the site as we have it. And we see if we go to the newest research, within the last week, we have 4,200 different papers. And so if we do a quick search for maybe spike protein. So what COVIDScholar will let you do is it will let you sort by research that is solely about COVID-19. It will let you sort by peer-reviewed or preprint research. We've tagged research with a number of tags on the topic. And if we go into one of these articles, we will suggest similar research that may have been overlooked. So these are papers that the NLP has detected as possibly similar. We also have built this fairly cool word embedding tool for exploring the word embeddings we produced on COVID-19. So each of these points in the cloud is something from the COVID-19 vocabulary, and their proximity to neighboring points is how similar they are in the literature, so how likely they are to appear in similar papers. And so if we again zoom in on spike protein, we can check out its neighbors. And you can see that we're starting to pull out things like other viral proteins, proteins in general, ACE2, which is the human protein that the spike protein binds to. And we will let users, using this, we can click on one of these points and we can go directly to a search from it. So just to hit you with, yeah, sorry. So just as a kind of guide of why field-specific research search engines are necessary, I pulled up this comparison of Google Scholar searches versus COVIDScholar searches. And so this is a search I did for spleen. This is actually a couple months old now. And so if you search for spleen on Google Scholar, it will come up with a variety of papers, none of which at first have anything to do with COVID. You can refine things a little more carefully and do a search for something like spleen COVID, and you get some somewhat relevant papers. But you can see here this first result on COVIDScholar. So all of these results are directly relevant to COVID. And this first result here, SARS-CoV-2 directly decimates human spleens, was a hugely influential paper that came out in March, and that's not even appeared in the first page of Google Scholar results. So this particular paper here got 51 citations in 6 months. It's been extremely influential. And if you were a researcher who was looking for information on COVID's effect on the spleen, it would be hard to find through Google Scholar, whereas for COVIDScholar, it comes straight to the top. This is something we can do because this is a search engine that is focused entirely on COVID. So we can build it around the needs of that research community specifically. So there really is a need for these domain-specific search engines, and they really are valuable. To give you a kind of breakdown of the sources of the documents in COVIDScholar, the majority of what we have comes from PubMed, which is a preprint server that gives mainly biomedical and medical preprints, but we have an enormous variety of sources. We have, at this point, I think 15 different sources distributed across a wide variety of fields. So it includes like the medical and biomed sources like medRxiv and bioRxiv, but also we have in here things like the Social Sciences Research Network, we have the National Bureau for Economic Research, we have SciArchive. So we have coverage of a wide variety of fields. They're not just the biomedical ones. And so to give you a little peek into how the COVIDScholar data pipeline works, so the pipeline that we have built has a web scraper for each of these sources. And then from these sources, we scrape them on a frequency of about once an hour. We scrape each of these sources. We pass the papers from these sources and we do metadata repair. And so often things like the citations of a paper or author information might be missing at first. And so then we will seek that out from multiple sources. And so we then combine all of these different sources of information on papers, which might be metadata, it might be a preprint and a published version. And we apply various NLP algorithms. So we do duplication, we classify them, we extract keywords. We put that all into a ground truth collection and it's searchable on COVIDScholar. And the timeline between a paper appearing on one of these sources online and all of this happening and it being searchable on COVIDScholar is it's on the order of hours. And so we use NLP models based on CyBERT, which is a BERT model variation, to give domain classification. We classify papers by their relevance to COVID-19. We extract keywords, and we recommend similar research. And I didn't want to get awfully bogged down in the details of these algorithms, but just to kind of give an indication of how well they work, I've plotted ROC curves for the domain classification problem. And so an ROC curve is a plot comparing the false positive rate versus the true positive rate of a classifier. And so the ideal classifier will have a false positive rate of 0 and a true positive rate of 1. So it will classify every paper that is actually about biological and chemical sciences, say, correctly, and not misclassify any other papers as about that domain. And so this black dotted line I've added here is the hypothetical perfect classifier. And you can see for most of these domains that the models we built perform really, really well. They have very low false positive rates and extremely high true positive rates. Perhaps with the slight exception of public health, which does still very well, although that's a little bit more of a fuzzily defined domain. And so these models are performing very highly in classifying COVID research. So BERT does a really good job of dealing with COVID research. Kind of the problem here is, even though we've built these amazing tools for putting papers into the hands of scientists rapidly, this is still more papers than any one person can read in a lifetime. To go back to the plot that I showed earlier of the cumulative publication count, by this point, there's over 50,000 publications on COVID. The average scientist can read maybe 10 to 20 papers a week. There's just no way that anyone can ever stay on top of these papers, even if they are getting only the most important papers directly sent to them. And this is not just a problem with COVID. The rate of scientific research in general has been increasing exponentially for quite a few years now. And we're now at the point where research is emerging sufficiently quickly across domains that domain experts are having a lot of trouble staying on top of them. And so the direction we're trying to take COVIDScholar in now is trying to see how we can use NLP to produce insights automatically from an enormous number of papers, more than any human could possibly read. And so we're trying to learn from the information contained in thousands of papers at once. And the way that I'm going to talk about that we've started doing this is going back to the word embeddings that we've produced earlier. So word embeddings are a way of encoding the vocabulary of your text as a vector. And so that will take in all of the vocabulary across all COVID publications and turn that into a set of vectors. And it does that in such a way that similar concepts lie close together in the embedding space. So if you look at this example I pulled out here, say cytokine and chemokine appear very close together because they're similar concepts. And so this is a technique that has let us integrate all of the information from all of the COVID literature into a single data set. And so there is this kind of famous result from the early days of Word2Vec, which shows that these word embeddings encode, they encode meaning and what you might call human intuition. And there is this result that these word embeddings are capable of doing analogies. And so an example might be if you say Paris is to France as Italy is to what? And the concept we're getting at here is clearly capital of country. And so the answer is Rome. And so if you take your word embeddings, which are vectors in some embedding space, and do this subtraction, so you say Paris minus France plus Italy equals what? You actually find out that the resultant embedding for that is the resultant vector you get from that is very, very close to the embedding for Rome. And so these vectors have encoded the concept that countries have capitals into a direction in the embedding space, which is kind of illustrated on this plot here for another example where the analogy is king is to queen as man is to what. And so the concept we're getting at there is gender. And you're able to show that within the embedding space, there is a direction that represents gender. And so the vector that takes you from king to queen is the same as the vector that takes you from man to woman. These are parallel vectors. And so there's a vector in embedding space that you can add to a word embedding that encodes the concept of gender. And so this is kind of a suggestion that these word embeddings are actually capable of learning something about the text we've given them. They're encoding knowledge about meaning. They're not just encoding knowledge about like grammar or syntax. There's actually some semantics to be had from digging into these. And our previous work in material science, we've been looking at these for materials, and we were able to show that these Word2Vec embeddings actually learn latent scientific knowledge. And so the plot I have shown here is the word embeddings that we produced from material science papers. And we've done a clustering. So this is similar to the embedding projector I showed earlier. This is similar embeddings close together on this plot. And what we were able to show is actually that materials with similar applications lay close together in embedding space. And so like we have a space here in embedding space where all of the superconductors, so all of the embeddings for all of the materials that are used as superconductors lie very close together. And similarly for battery materials, thermoelectrics, intermetallics. And so quite surprisingly, we were able to show that this sort of simple NLP technique was able to learn scientific knowledge and was able to tell us things about science. And the way we took it from there is to say, okay, so if this cluster here is all of the thermoelectrics that are known, what are the materials that lie close to those? So what are the materials that the word embeddings say are similar to existing thermoelectrics, but have not yet been studied as thermoelectrics? And what we were able to show is that if you use these as predictions for the upcoming thermoelectrics, so if you take, say, all of the papers published before 2015, and you say, do the word embeddings on those, tell me which of the materials which lie closest to the thermoelectrics that haven't been studied as thermoelectrics, we're actually able to find that that was accurately predicting the new thermoelectric materials years in advance of their actual study in the material science literature. And so this plot here is showing the percentage of the thermoelectric predictions that went on to be studied as thermoelectric materials after a certain number of years after the prediction. And so when we go up to 17 years after the prediction, 40% of the predicted materials actually turned out to be thermoelectric, which is incredibly surprising. So these word embeddings were not only able to absorb the scientific knowledge in the text that we were given them, they were able to make these connections across many, many papers and suggesting that say, this material is similar to another material in this way. And if that material has been used as a thermoelectric, then maybe that one should be, the first one should be used as a thermoelectric too. They're able to make these connections, and they're able to provide genuine scientific insight in a way that utilized the information of literally millions of papers well beyond what a human could read. And so we've been kind of looking at this for COVID applications. And so something we've started to work on is the first example we worked on was seeing if we could predict virus host interactions using the COVIDScholar word embeddings. And so the question we are asking here is, which of the human genes have word embeddings that are closest to the embeddings for COVID-19 proteins? And so this is an extremely important question for understanding the mechanism of virus interaction, understanding the protein-protein interactions between viruses, because once you understand which human proteins virus proteins are interacting with, you can start to develop antivirals which will target the action of those proteins. So this is a very important question. And so we took our embeddings from COVIDScholar and we found that we have at least 2,600 human genes with at least one mention in our text corpus. So these are all of the human genes that have been mentioned at least once in all of the COVIDScholar collection. And then we said, okay, so which of these are closest to the embedding for the 30 COVID-19 viral proteins? And so we took each of those 32 COVID-19 viral proteins, we took their embeddings, we found the cosine similarity, which is a measure of similarity between vectors for each of those, and we found which ones are predicted to be the closest. And the top candidate we found is this gene called mortality factor 4-like 1, which has a cosine similarity of 0.91 to the COVID protein embeddings. And just to give you some context, this is quite close. If you do a comparison, the similarity between the word embedding for coronavirus and for MERS is about 0.92. So these are diseases which are known to be very similar. And so this is suggesting that this human gene is very, very similar to the COVID-19 proteins. The word embeddings are predicting a relationship between them. And so we dug into the literature after that, and we found this paper that predates COVID. This is not in the COVIDScholar collection, talking about this protein. Mortality factor 4-like 1 protein mediates epithelial cell death in a mouse model of pneumonia. And so in particular, there is this comment in here that this existing antiviral argatroban is a mortality factor 4-like 1 antagonist. And this is already somewhat promising because this is talking about epithelial cell death, which is known to be important in the mechanism of COVID. And it's talking about a different viral disease, pneumonia, which has in some senses similar action. And so if we look at this drug argatroban, it actually turns out that there is an existing clinical trial utilizing it to test COVID-19, which is now in phase 4. And so this was not information that was included in the COVIDScholar corpus that we use to produce text embeddings. So on their own, NLP produced word embeddings trained on text with no direct relationship, with no direct mention of any relationship between COVID-19 and argatroban or COVID-19 and mortality factor 4-like 1, or even between argatroban and mortality factor 4-like 1. We're able to predict that this existing antiviral was perhaps a useful target for drug repurposing for COVID. So I have to stress that this is an extremely preliminary response. I don't want to make grand claims about the value of this in isolation. I think this is a promising example of what can be done. And I think ultimately the way moving forward that we're going to be using this is using this as, I guess, an ideas generator for scientists. So we're not aiming to be at the point where NLP can directly suggest a new drug to be targeted for repurposing, where we're going to be building tight feedback loops between scientists and the NLP, where we're giving them suggestions of a list of genes they might think about, and maybe that will prompt something that they hadn't thought about or something counterintuitive. And so this is very much an aid towards scientists. It's not replacing scientists, but these are exciting and promising results. And so looking forward, we have these like quite promising initial results for latent knowledge extraction. We now need to dig into formalizing this approach a little more. We've only just started to do this now that we have a good text collection built up and we're collecting papers. And this extends well beyond just papers. I mean, scientific data is in general unstructured and heterogeneous. We need to find new ways of engaging with all sources of data and integrating all sources of data, because the amount of scientific data is just absolutely exploding. And there's currently not good ways of integrating, say, the knowledge that is contained in papers with the knowledge contained in clinical trials, with the knowledge contained in databases of protein-protein interactions. And we need to do this building tight feedback loops between scientists and AI. Ultimately, we need to build this specifically for the needs of scientists, and we need to integrate their feedback continuously to develop the AI tools. And the goal here is never to replace scientists with AI. The goal is to use AI as a tool that will let scientists integrate information from many thousands of papers or many thousands of data sources that they couldn't have otherwise read. And this is relevant well beyond COVID research. We've been doing this in the context of COVID because for a lot of reasons, it's a good choice. It's very urgent, it's very pressing. There's an enormous amount of data, but the increase in the amount of scientific data is something that's becoming an issue in many fields. And so longer term, this is kind of pushing towards a new way of doing science. This is a way of doing science that changes the way we engage with the scientific literature, that is less about finding specific papers of interest and reading them, and more about automatically integrating insights from many, many papers. And so the work we're doing so far in the context of COVID, we've been integrating the embeddings from COVIDScholar with the KG COVID-19 project, which is a project to build knowledge graphs about COVID, using various data sources. So these are things like databases of proteins, of drugs, all of these things. So these are quantitative databases with connections between them. And so what we've been building is a connection between the word embeddings that we've extracted from literature, the COVIDScholar embeddings, to the information contained in these databases. And so we're linking that. And so on the simpler side, we can now do things like say, if you find this row in a database saying some information about a drug, we can give you the papers specifically that talk about that. But ultimately moving forward, we're going to be combining all of this information into machine learning models, using embeddings derived from both the database information and from the text to produce strong classifiers that integrate as much information as possible. And that's kind of all I have time for. I just want to thank the COVIDScholar team for all of their incredibly hard work. Everyone put in ridiculous hours to get this running at the start of the pandemic. And people are doing this for, this is not, this is a number of grad students doing this without progress towards their thesis. People are doing this entirely because they care about the COVID response. And I just want to thank them for all of their hard work.
Thank you very much for a great presentation. We have a few questions that have been answered already, but there is one question that has not been, a couple, but the one that is kind of very interesting is there a way to run a search and identify areas where more research is needed? I guess this goes towards understanding. So maybe you can comment on that. Yeah,
that's a great question. And it's certainly something we've thought about. And so in the context of material science, we've started trying to apply this. This is not something we have yet started doing for COVID, but the idea behind what we're doing is basically to build up the word embeddings from the extracted literature and use them to say things like, what are the concepts that these embeddings would consider similar that have not yet been studied in text? And so for material science, maybe it would be like, this material is predicted to be similar to this synthesis method, but no one's reported it being synthesized in that way. Does that mean that this is a promising approach to take? Does this mean that there's some issue there that's not reported in the text? So yeah, that's something we've definitely thought about. And I think moving forward, that's going to be something that's quite valuable that we can produce from this.
Very good. Another question is has to do with potential biases in the system. The question is, the feedback from scientists can be biased. How are you going to manage that?
Right. I mean, ultimately, we can't teach AI to be better than the scientists that produced it. AI is only capable of automating the work of scientists. It's not capable of removing those biases on its own. I guess the only, well, sort of the best answer I have to that is that when you produce word embeddings from like 60,000 papers, you are averaging over the bias of 60,000 different authors. And so things that are idiosyncratic to particular scientists get sort of evened out across that. I don't think we have a way of dealing with community-wide bias.
But maybe to add one thing, I think one thing we have found, right, is that it, as Amalie says, it cannot remove bias, but where it is unbiased more sometimes is in telling you in new directions to look at. Like, I know that when we did this in the material science, we would sometimes look at connections, which yes, sometimes were totally false and not good, but occasionally were worth pursuing and we would have never come up with them ourselves. So it's a sort of, I think there it helped us overcome our own bias about what is an interesting direction or solution.
Very good. Another question has to do with the named entity recognition. The question is, what model do you use for that?
So we used a model that was based off Cybert's embeddings. And so we fine-tuned that with an NER model on our data. We found that to perform pretty well. There's a number of different BERT variations out there for scientific text. We found Cybert was the best one. But moving forward, we're kind of looking at pre-training our own variation of BERT on the COVID text, since we now have enough of it that that's possible.
Very good. And there is a comment from Stefano Bertozzi, which I'm sure all of you know, about connecting together. Stefano, maybe you want to comment on that. Apparently, you're using similar techniques for reviews. Let me see. Maybe, I don't know if how to give you voices, Stefano, apologize.
Maybe I mean, I don't want to speak on Stefano's behalf, but I can perhaps like fill in a little bit more there. And so, oh, there's Stefano. Okay.
Well, Amalie can definitely answer better than I can, but they've been incredibly helpful to us with the Rapid Reviews COVID-19 journal, because not only have we been taking advantage of their scraping capabilities, but the nearest neighbor work has been incredibly useful to us, because our job is to rapidly identify peer reviewers, and by identifying nearest neighbor papers, you're also identifying nearest neighbor authors. And my hope is that over time, we can do even more work in terms of prioritizing those nearest neighbor authors, both by the disciplinary overlap with the actual work in the paper that we're reviewing, in the manuscript that we're reviewing, given what we know about their work on other papers, but also in terms of seniority and other things like that, so that we can provide to the people who are choosing peer reviewers the best list. And since you gave me the microphone, I was just going to comment on this, on the bias issue. I think it's a really interesting question. And while I completely agree that you can't unbias the biases that exist, because those are the data that you're working with, it might be possible, given that you're drawing from the whole world, to look differentially at the degree to which somebody cites somebody who's in their collaboration network, rather than something that is equally close in terms of the space that you're mapping, who's not in their collaboration network. and the degree to which that means that the R1 universities or tend to cite each other more than equally related work from across the Atlantic or from the Pacific or whatever. I think it might be interesting to see if you started to pull apart that those 60,000 papers by who is already working with whom, you might be able to get a handle on the degree to which people are biased to the people they know and that are close in, that are evaluated by the same evaluation bodies, et cetera.
Interesting. I mean, one can see that we can take the art of peer review and turn it into data-driven science, right? This is what you're going towards. That's quite exciting. And of course, I'm sure a bit controversial too. Excellent presentation. I don't see any other open questions, but I would like to open the forum. Oh, here it is. There is a question by Yongshu Zhu. Inspiring and striking, he characterized the work. What will the general topic search engine be? When will a general topic search engine be available for use?
Oh, so that is the COVIDScholar website? That's what you're talking about?
I presume so, but they're talking about the general topic search. General topic search.
Like across scientific literature?
Apparently, maybe you can clarify, but that's how I read the question.
Okay, so maybe I can comment a little bit on that. So something we've found is that the real value in this lies in finding a happy medium between doing this on a large enough scale that this is integrating a lot of research, but doing it on a narrow enough topic that there's some consistency within the work. Something we found in our material science work is that as soon as you start including papers that are even slightly irrelevant to material science, the quality of the results you get from NLP degrades. And so I think moving forward, the approach here is not that we're going to eventually produce one website to sort of rule them all and do all scientific publications. I think it's about having a multitude of websites that are field specific.
Very good. Any other questions or comments from the audience or from the panelists? All right. Well, at this point, I would like to thank our speakers for an excellent presentation. Actually, quite. Stefano, you mentioned something topic specific, but pan-discipline. That is actually an interesting distinction that he's making. Mm-hmm. Right, COVID-19, but go by multiple disciplines. Can you comment on that?
Yeah, I mean, this is kind of our whole motivation for doing COVID-19 is to deal with a topic that has publications across an enormous variety of disciplines. And a big issue that we found, especially talking to our colleagues in social sciences, that there is an issue that multiple disciplines will end up studying the same thing, but people will only read publications from their own disciplines. And so they won't necessarily see research and they'll end up replicating it, or they won't have possibly valuable results. And so, yeah, totally agree with Stefano that the value here is being able to suggest to them, like, you're a behavioral scientist. Have you maybe looked at this research from economics that might be important, or from public health that might be important? It's about suggesting research that might have otherwise been overlooked.
Very good. Not seeing any other questions. I think that is a good time to end with a very nice comment. I suppose that this was a great talk. So thank you all, and I hope to see you. I hope to see you again in about a week's time. Thank you.
Thanks.